In this lesson, we'll learn how to do the calculations for correlations and simple linear regression using Excel. This lesson again is brought to you by Uncle Frank. Imagine that the fantastic faculty at a very high prestige nursing university, School of Nursing, had developed a scale which they thought would help predict how well students would do, first-year nursing school students would do in their first year of school. And they call that score the hardiness score. And they're using it to predict how well students will do. Now, they might ask themselves, is there a linear relationship between the hardiness score and the GPA of the nursing students after the nursing students' first year of school? So imagine that we're going to use our regression techniques and our statistical ability to answer this question. Here's the data. The first student had a hardiness score of 0.68 and a first-year GPA of 2.61. The second student had a hardiness score of 0.79 and a first-year GPA of 3.49. So the first thing we would do is we would take data and we would enter it into our spreadsheet. And you'd notice a couple things funny. Even though you might type in just 0.68, Excel's going to add the leading 0. It's going to add 0.68. So there's no need for you to type the 0.68. It's a waste of a key typing. So you can just put 0.68 and it'll put the leading 0 in front of it. Another thing you might notice, like in A12, is when you type in 0.70, it leaves off the following 0. It just, even though you've typed in 0.70, once you hit enter, it'll change it just to 0.7. Now, that won't change your answer, so don't let that bother you. But don't keep trying to retype it thinking there must be something wrong. No, that's just the way Excel works. We could change that if we wanted, but it's not worth doing right now, so we won't. So now we're going to try and work this problem. And instead of going up to tools and going to data analysis as we normally do, we can do this one straight with statistical functions. So we'll do that. Here are the functions that I want to use, or the answers I want to derive. I want to derive what R equals. R, remember, is your Pearson product moment correlation coefficient. It's easier to calculate than it is to even say. The next thing we want to do is the slope of our regression line. So we'll have our best fitting line that goes through our dots. I hope you've been playing the correlation game that's on the web where you're trying to guess what the slope is of a line or trying to draw the best line through the dots. But anyway, that'll be our slope of our regression line. We'll also calculate the intercept of the regression line. Skipping down to the bottom of that column, once we've got the slope and the intercept, we can get our specific equation. The general equation for a line is y equals a plus bx. But to get a specific equation, we need to know what a is and what b is, and we'll find out what those are. Then we'll find out what our coefficient of determination is. That's just r squared. And then we'll build a little formula box where we can put in any value for hardiness score. And this will tell us what our regression line would tell us would be the predicted grade point average for that hardiness score. So I know that sounds hard, but it's not that hard. We'll start with the first one. All we do to find out what the Pearson product moment correlation coefficient is we type an equal sign, then C-O-R-R-E-L, which is short for correlation, then left parenthesis, then we put in our data range for our y values. Now, it's not so important with an R, but later when we do the slope-intercept, it's very important that we do the y values first. So we'll do it here too. The y value is the thing that you're trying to predict. We're trying to predict the grade point average. So we want to put in that column. So we'll put in B2, not B1, because when we're using functions, we can't include the label, so we have to just say where the data are. So we put in B2, a colon's a dot over a dot. I know you nurses think of a colon in an entirely different way, but for Excel, a colon is just a dot over a dot. And then we'll go down to B16, which is the last place our data are. Then we put in a comma because we've ended our Y range, and now we put in our X range, which is A2 colon A16. Then we close our parenthesis, and when we hit enter, our correlation is 0.5943. So that's pretty good. That wasn't that hard. Slope is even easier because we do it exactly the same way we did our R, except we replace the correl with the word slope. So our magic word is slope. So we just type in equal sign, slope, parenthesis B2 colon B16, comma A2 colon A16, and enter parenthesis. Then when we hit enter, we'll find our slope is 4.0748. That's a pretty steep slope, and it's positive. So that means that as hardiness scores are higher in value, GPAs are higher in value according to this regression line. In fact, for every 1 unit change in hardiness, there's a 4-unit change in GPA. So that's pretty big. The next thing we'll calculate is our intercept. There, the magic word is intercept. So we type an equal sign, the word intercept. We put our data range, which is parenthesis B2 colon B16, comma A2 colon A16, and enter parenthesis and press enter, and we get 0.0512. No, 13. 0.0513 when I round it off to 4 decimal places. You know, now that we have the slope and the intercept, we can skip down to our equation for the line and put what the equation is for our specific line. Again, the general equation for a line is y equals a plus bx. But we can replace what a is and b is because a is the intercept and b is the slope. So we'll do that. We end up with y equals, our a is 0.0513 plus bx, but our b is our slope of 4.0748, and then we have to follow that with an x. So this is the equation for our regression line. Now let's go up and find out what our coefficient of determination is. Now remember what that is. That's what percent of the variance in GPA can be explained by the variance in hardiness. That's the coefficient of determination. But all we do to calculate it is we take our R value and square it. So to do that, we type in an equal sign, and then we could type in E3, or we could just click on E3. But then we have to type in a caret. A caret is shift 6. Shift 6. It's the 6 that's above your letter keys, not the 6 that's on the number keypad. So you have to go shift 6, and that'll give you that caret. And then that's saying raised to the power of, and since we're squaring it, that means to the power of 2, so we follow it by 2. So we type an equal sign, click on E3, press shift 6, then we press 2, and then we press enter, and we get 0.3532. And you might be saying, wait a minute, why did it get smaller? Normally when you square things, they get bigger. Like if you square 2, you get 4. Square 3, you get 9, your numbers. Well, if the number you're squaring is less than 1, you'll actually get a smaller number. 1/2 squared is 1/2 of 1/2, which is 1/4. So it's a smaller number. So whenever the number you're squaring is less than 1, you actually get a smaller number when you square it rather than a bigger number. Okay, now we're to the last step here. Here we're going to say if x equals some value. Let's just make that value 0.75. I just picked that out of the sky. So let's say our x is 0.75. What would our y be according to our equation? So we're just going to go over to cell G6 0.7 and type in some commands, just an equation, that'll always give us the right answer, no matter what we put in E7. So let's give that a shot. What we'd do, our equation is y equals 0.513 plus 4.0748x, and our x is what's ever in E7. So we'll just put this in Excel terms. So what we'd do is we'd type an equal sign, then we'd click on cell E5, or you could just type in E5, whichever one's easier for you. Then type in a plus sign, then a left parenthesis, then we could type in, or we could actually just click on our slope, which is 4.0747. In other words, whatever number is in E4. So you either type in E4 or you click on E4. And then you put an asterisk, which means multiply. And asterisk is Shift 8. Then we're going to click on E7, which is where we're putting in our x value. Then we close our parenthesis and press Enter. Now once we've done that, that'll tell us the predicted value. That's saying if a student came to us and we knew their hardiness score at the beginning when they started the school was 0.75, then we'd predict their first year GPA to be 3.10. Now you might be saying, but wait a minute, if I look over there on the left, there is a student got 0.75 hardiness score, and his or her GPA wasn't 3.1073, it was 3.42. Well, that's because our predictions aren't perfect. They're just not perfect. If our R score was 1, our predictions would be perfect, even if it was a negative 1 for an R score. But if our R is, if the number following the sign for our R score is less than 1, then our predictions won't be perfect. Let's type in another number where the 0.75 is. So we're going to say, let's try 0.68. So actually, let's take a look. We've got 3 students that have 0.68. So we'll take a look at those before we'll type it in and see what we predict. There were 3 students who got a hardiness score of 0.68. The first student had a GPA at the end of the first year of 2.61. The second one, though, got a different GPA, 3.1. The third student got even a different one, 3.05. So that means these students differ maybe in how much other responsibilities they have, how much effort they put into school. There's a lot of different things that will affect their GPA, not just their hardiness score. So all these different students, even though they start out with the same hardiness score, they're going to get slightly different GPAs. Let's now put in 0.68 and see what our equation would be. So we'll just type 0.68 in cell E7, and then when we hit Enter, the number in cell G7 will automatically change to match our new number. So our regression line would predict a GPA of 2.82. So our regression line predicted a higher GPA than the first student actually got, but a lower GPA than the second or third students. So our guess is kind of in the middle of those students. It overguessed the GPA for 1 and underguessed it for 2. So it was pretty reasonable. And that's kind of what a regression line is the best fitting line that fits in the middle of all your data. Okay, so now we have all this information. Let's do some hypothesis testing to see if this is significant, if this much of a difference and our score of this high for a sample tells us that there's a difference in the population. Our hypothesis testing step, I always start with step 2, just because I'm weird. Start with the alternative hypothesis, and that's that rho, that is, rho looks like a P, but it's really the Greek letter for R, and it's spelled R-H-O, and pronounced rho, even though it looks like a P. But what it really means is the correlation of the entire population. So if we had all the members of the population and calculated a correlation rather than just a sample. And in this case, we're saying it would not be 0. In other words, there would be a relationship. We could write now the null hypothesis, or HO, which is just that rho equals 0. In other words, if it doesn't not equal 0, then it must equal 0, and those two things cover all possibilities. Now let's go to step 3. In step 3, all we do is we set our alpha, and we'll use the conventional 0.05. So we'll say alpha equals 0.05. This is almost what it always is set at. Sometimes they'll use 0.01, and in very rare cases they'll use 0.001, sometimes 0.1, but almost always 0.05. So we're going to go with 0.05. Now we do our rejection rule. And step 4 is rejection rule, reject the null hypothesis if the absolute value of R comp is greater than or equal to some number. Now where do we get that number? Well, in this case, it turns out it's probably easiest to get it from the appendix in the back of our statistical book. Now, at the time of the recording, at this present time where I'm recording, table is table E, but since the editions of the books changed, it may be different for you, but there should be a table that has the critical values of R scores, and here's what it looks like at the present time. It tells you that the degrees of freedom equal n minus 2, where n is the number of pairs of scores. Then it's got a column for degrees of freedom. It's got a column for the 5%, which is the same as 0.05. And it's got a column for 1%, which is the same as 0.01 for an alpha. So if the degrees of freedom are n minus 2, and we had 15 scores, well, 15 minus 2 equals 13. So we have to go down our degrees of freedom column until we come to 13. I've underlined that row in red for you. So our degrees of freedom are 13, and our alpha was 0.05, so we go to the 5% column, and we find our critical value is 0.514. So this is what we put in our step. So our rejection rule is reject the null hypothesis if the absolute value of R comp is greater than or equal to 0.514. Now, next step is to do the calculation. Computation and test statistic. What does R comp equal? Well, we've already done that. So let's just look at our spreadsheet that we've already done, and we'll see that we found that R was equal to 0.5943. So we'll just move that and put it in our table, 0.5943. Now we have to make a decision. Let's remember our R comp is 0.5943. That's the absolute value of our R comp as well. So our rejection rule, step 4, said reject HO if our R comp is greater than or equal to 0.514. And it is. So we get to reject our HO. So step 6, we just write reject the null hypothesis. Now step 7 is a 3-step final statement, conclusion. So we always start with whether or not we'd reject it. We always start by saying what our alpha level is. So we would say at an alpha level of 0.05. That's just the way they always start. At an alpha level of 0.05. Now we have to say what we found. And what we found was that there is a significant direct relationship. Direct because our R score is positive. So at an alpha level of 0.05, there is a significant direct relationship between students' hardiness scores and their first-year grade point averages. So that's the first 2 of the 3 steps we need for our conclusion. Well, we start with at an alpha level, then we say what we found, and next comes the statistical string. The statistical string always starts with telling what kind of statistic we calculated. We calculated an R, and then for R's we have to say what our degrees of freedom are. So let's take a look at that. Our degrees of freedom were 13. Remember, we had 15 pairs of scores minus 2 gave us 13. Now, to get the next thing, is we just say what our R value ended up being from step number 5. In our case, it ended up being 0.5943. Now, you might wonder, why am I not putting 0? Why am I not putting 0.5943? That has nothing to do with statistics, has nothing to do with nursing. It has to do with APA format. In the APA format, it says if you have a number that can never go over 1, and R scores can never go over 1, they can never be greater than 1, neither can probabilities, neither can alphas. If they can't be greater than 1, you don't put a leading 0. So our slope would have a 0 in front of it if it was less than 1, because slopes can be greater. Our intercept, because intercepts can be greater than 1. But R scores and correlations and probabilities, none of those would have the leading 0. So after our comma, now what we do is we put our probability, our p-value. But we don't know exact p-value like we did before. But we do know that we rejected it. And since our alpha is 0.05, we know that to reject our null hypothesis, our probability of being wrong must be less than 0.05. If it were more, we wouldn't risk doing it. So it must be less than 0.05. So we'll just put p is less than 0.05. And then finally, we'll put that this was a two-tailed test at the end. So that's the way we would write our steps. But just for the fun of it, let's take a look at what would happen if we had had a negative correlation. We didn't, but let's pretend instead of having a positive 0.5943, we would have had a negative 0.5943. We still would have rejected the HO, but our conclusion would be different. We would say at an alpha level of 0.05, that stays the same. But following that, we would say there is a significant inverse relationship between students' hardiness scores and their first-year grade point averages. So the difference is in the word inverse versus direct. Inverse means that the higher the hardiness score, the lower the GPA is likely to be at the end of the first year. That's not the case. Let's also see what we would have done if we would have gotten a score that was lower than 0.514, so was not significant. What if we would have computed an R comp and it would have been 0.5043? In that case, our decision would be fail to reject HO, and our conclusion would be at an alpha level of 0.05, there is insufficient evidence to conclude that there is a relationship between students' hardiness scores and their first-year grade point averages. R parenthesis 13 end of parenthesis equals 0.5043, comma, p greater than 0.05. Actually, this would be, p greater than 0.05, because here we failed to reject. So that means our probability of being wrong must have been greater than 0.05. And again, it's two-tailed. In the next lesson, we'll learn how to do a graph of this data and to plot our regression line on that scatter graph.